I'm going to show how to use an interactive simulation that models ternary phase diagram in what we've called an alternate phase envelope. The simulation is located at the link given here, and I'm showing you a snapshot of the simulation where, remember, for ternary phase diagram, the corners, pure component A at the top, pure component B at the left bottom, and pure component C at the right bottom. For this diagram, this region here consists of two phases, so we separate liquid into two phases that are in equilibrium. And the black dot shows the point that we're located. The overall composition we can read off the diagram, but what we're showing is the composition of the alpha phase, the orange point, and the beta phase, the purple point, that are in equilibrium. And when the black point is close to the orange point, then we have mostly the alpha phase. So let's look at the interactive simulation. So I've selected phases in the diagram to show we have single phase in this region and this region, and then in the very large part of it we have two phases in equilibrium, and those two phases are on the orange line and on the purple line. They're connected by tie lines, and that's what we're showing here are the tie lines. So I could remove those in the simulation to make it less crowded. Likewise, I could add grid lines or remove them, make it less crowded. Grid lines make it a little easier, for example, to read the composition of this black point, the overall composition. And if I move the point around, what the simulation does is show you the composition of the two phases at equilibrium. It doesn't tell you how much of each phase. So if I move along a tie line, then the compositions won't change, but the amounts of each phase will change. Now I can remove this, and you can test yourself by making sure you can read off what are the compositions of these phases are in equilibrium. So important to understand three-component system that we can have significant range of compositions where we have phase separation.